Today we're going to take notes on centripetal acceleration. And when we're talking about centripetal acceleration, we do need to take into account Newton's second law. And that states that any external force, net external force, acts on an object of mass m. Its acceleration is directly proportional to the net force and has a magnitude that is inversely proportional to the mass. That direction of the acceleration is the same as the direction of the net force. This can be seen in the equation A equals F over m, which is taken from F equals ma, which we all know that equation. Centripetal acceleration is how quickly an object's velocity is changing in a circular motion. It is center-seeking, which we already explained in the last slide, and that it points to the center. The equation is A sub c equals v squared over r. And remember that v equals 2 pi r over the period. And when you plug that all in, you will get 4 pi squared r over t squared. We mentioned centripetal acceleration is center-seeking, and in that it points to the center. As the object moves about the circular pattern, so in this circular motion, the velocity changes. Therefore, we are always having acceleration. If you find the resultant of the velocities, so here we have v1 and then we have v2, if you find the resultant, you will actually find the change in velocity, and what you'll notice is that the change in velocity is center-seeking, and this is the acceleration, which is also pointed towards the center. Circular motion can be horizontal. For example, a car is turning on a level surface. When you're looking at the free body diagram over here, what you'll notice is that the forces acting on the car are its weight, which is mg, and that is pulling down. We have the normal force, which is denoted as N. However, we also denote that as the capital letter R, and that is due to the road pushing up on the car. Both of these forces act vertically and have no horizontal component. The friction is pointed inward towards the center. The friction between the tires and the road causes an unbalanced force, and this centripetal acceleration is also towards the center. The friction provides the centripetal force that keeps the car turning. If that frictional force was not there, the car would just slide off and not be able to turn. Here's an example for you to try. A 100-kilogram moving car is turning around a circle radius of 20 meters. Determine the speed of the car. Go ahead and try to solve this problem and then start the video back up. Step 1 is to draw a free body diagram, and remember to label this with both words and symbols. When you're drawing this, what you'll notice is that you have the normal resistive force, denoted as R. We have the force of gravity, or weight. And we have the friction force that is either in whichever direction you decided you wanted to make your car turn. For me, I went that my car was turning left. And I also placed that the acceleration is also to the left. I pushed it away from the force of friction just so that you can actually see it and it's not overlapped, but the acceleration and the friction force are in the same direction. Step 2 is to find the net force. Then you can substitute using the centripetal acceleration equation, solve for v, and you would have your answer. The variables that we have are listed over here on the left, and we are actually trying to find the speed. Using the equation F equals ma, and knowing that acceleration equals v squared over r, we just plug in this v squared over r into our F equals ma equation, and when we plug in our values, we solve for v, and we get an answer of 10 meters per second. Circular motion can be at an angle. For example, if you're driving on a banked curve, which looks like this picture on the left, the normal force is always perpendicular to that of the incline, which is true for any incline problems that we work with. On a frictionless banked curve, the centripetal force is the horizontal component. which is located right here, and it is going towards the center. The vertical component of the normal force balances the car's weight. And so, as you can see, which is true for all our previous problems when solving for objects at an angle, we have to take into account the x and y components. For example, a curve has a radius of 50 meters and a banking angle of 15 degrees. What is the ideal or critical speed for a car on this curve? In my free body diagram, I made my car turn to the right. So we have the frictional force vector to the right, and we know that the frictional force is the centripetal force. We have the angle, theta, being 15 degrees, and we know that the normal force here, and it can be solved by the x and y components. We know that the direction of the acceleration is the same direction of the net force, which is inward towards the circle. Because we know acceleration is caused by a net force, and that net force causes an object to take a circular path, which is inward seeking, we know that the net force equals the centripetal force. We also know that the friction force provides the centripetal force, so we can say that the frictional force equals the centripetal force. Therefore, we know that the net force equals the centripetal force. To find the net force, we have to find the normal force, which is the tangent, theta, times the weight. And we know that the centripetal force is equivalent to mv squared over r. To get this part over here for the net force, all you had to do was to find the components. We know that this component here, the x component, the horizontal component, is r sine theta. We know that this component over here, because r equals mg over cosine theta, we can just plug that into the x component, and we get a net force of mg times sine theta over cosine, and sine over cosine is tangent, therefore your net force is the weight times the tangent of theta. And then we just equal it to mv squared over r. When we solve, we get a speed of 11.464 meters per second, or 11 meters per second after taking into account significant figures. Circular motion can also be vertical. For example, if you're swinging a bucket of water around, or if you're riding a motorcycle or other vehicle into a hollow metal cylinder, and it also, what you'll see is that there is a circle, there is a radius, and you will have to have a certain amount of speed in order to keep that circular motion. Let's look at the vertical motion a little bit more closely. We want to know what's happening with the forces at each of the points of the bottom, the top, as well as the sides. What we know with an object that is moving around a circle vertically is that its tension or its centripetal force changes, its net force changes depending on where in the circle you are. We know that the net force equals the centripetal force, and it is center seeking. We also know that the centripetal force equals mv squared over r. So when we set that to each other, we know that the net force equals mv squared over r. We know that the net force changes as you go around the circle depending on where you are. In order to find the net force, let's start at the bottom. We know that we have one vector here as the weight, and we have the force, the centripetal force, or here the tension if you were taking, example, a string in an object and vertically swinging it around into a circle. So we have two opposing vectors. We have the weight minus that of the tension of the string. If you solved for the tension by just moving over the weight, then you would get the tension equaling the weight minus mv squared over r. For the sides, and that goes for both sides of an object that is moving in a circular motion, because the directions of the forces are the same as an object moving in a horizontally circular path, We just use the equation T equals mv squared over r. At the top, what you will notice is that the weight is going down, as usual. However, the centripetal force and the net force is pulling in also, which is down in this case. So when we take that into account, we know that the net force is going to be the gravity plus that of the tension, which in this case are going in the same direction, therefore we add them. And we set that to mv squared over r and solve for the tension, giving us mv squared divided by r minus the weight. Here is an example. A 2-kilogram bucket with water is swirled around a circle radius of 1 meter. The speed of the bucket of water is 2 meters per second. Determine the tension forces that keep the object in circular motion at the top and bottom points. Go ahead and try to solve this and then start the video back up. The first step is to list the known values. We know that the mass is 2 kilograms, the velocity or the speed is 2 meters per second, and that the radius is 1 meter. Here is just a simple diagram. And what we want to do for each of these 2 points is to draw the free body diagram. What that looks like at the bottom is that the force of gravity, or the weight, is going down, and it is smaller than that of the tension force. And therefore, I make the tension force a little bit bigger. The acceleration is also inward seeking, therefore it is going in the same direction as the tension force. For the second part, which is up at the top, we have both forces going inward, which is downward, into the center, and the acceleration is also following. Step 3 is to calculate the tension, the force of tension at point 1. And remember, what we need it to do is just to set the net force to that of the centripetal force. And at the bottom, what we have, because the vectors are opposing each other, we would take the weight minus that of the force of the tension of that string, and we would equal that to the centripetal force. When we solve for the tension, we get an answer of 28 newtons. This means that it's going to take 28 newtons of force to keep that bucket in a circular path. If it doesn't have 28 newtons, then the bucket will lose the water that's inside of it. It will not be able to keep itself in that circular motion. The next step is to calculate the force of tension at point 2. When we solve for this, remember that each of the vectors are going downwards, therefore we add the 2 units. We set that equal to mv squared divided by r, which is the centripetal force. We solve for the tension, and we get an answer of 16 newtons. And that just pretty much means that it's going to take less force to keep that bucket in a circular path at the top of the motion versus that of the bottom. Here's another example. Go ahead and try this and then start the video back up. A stunt pilot of mass 80 kilograms flies in a vertical circle of radius 350 meters at a constant speed of 70 meters per second. Calculate the force of the seat on the person inside at the top of the circle, at the side of the circle, and at the bottom of the circle. So just remember, this picture here is to help you to remember how to add or subtract your weight from your tension. And here are the answers. When you solve for the top of the circle, the force at the top of the circle, after plugging everything in, you get an answer of 335 newtons. At both of the sides of the circle of the pilot, he will be needing 1,120 newtons of force in order to stay in that circle. At the bottom of the circle, the tension that that person is feeling, or the force, is 1,905 newtons. The big concept to know and be able to explain is that it takes more force at the bottom to keep an object in motion vertically, in a circular motion. Okay, so we are finished with our notes. Please look on Haiku for any further instructions. Always know that you have the online textbook and the review questions in there in order to practice, as well as your textbook, the study guide. You have so many resources. Other than that, have a great day. Thanks for watching.